Hey everyone, welcome back to vBrownbag US. Tonight we have Shane Walton presenting on Data Center Unified Fabric. A few quick show notes. Get in on the conversation. Follow at vBrownbag or at vBrownbag Latam or at vBrownbag EMEA. And our Twitter hashtag is hashtag vBrownbag. So if you have any questions for us during the podcast or after, make sure you use that hashtag vBrownbag. We actually have a few different regional vBrown bags, if you haven't heard. One in the APAC every other Thursday, 10 p.m. NZDT. One in EMEA, currently running the VCP NV series, which is Tuesdays, 7 p.m. BST. Latin America, Thursdays, 7 p.m. PDT. And of course, the US, Wednesday, 7:30 p.m. Central. Our guest tonight, like I said, is Shane Walton at Shane_Walton on Twitter. And our host tonight, we have a new host, Brandon Graves at Brandon G08. I think I messed that up, but it is 08. Brandon, say hello. Are you there, Brandon?
Sorry, no mute. Hello, everyone.
All right. And I'm Lauren Malhoit at Malhoit. And I will pass the ball over to Shane. All right, Shane, do you see it?
I do. Can you see my screen?
We can. You are good to go. Thanks so much.
Great. Thank you very much for having me again. This is the CCNA Data Center series. This is the third one that I've done. This is Data Center Unified Fabric. My name is Shane Walton, and I am a Data Center Solutions Engineer. Today's agenda, we're going to continue going over the 649.16 test introducing Cisco Data Center Technologies. This is the second test in the CCNA Data Center test group. Today we're going to be describing data center bridging in Fibre Channel over Ethernet. We're going to describe virtual interfaces and fabric extenders, and then we're going to do a little bit into Fabric Channel over Ethernet multi-hop. As always, this is introducing Cisco Data Center Technologies. Most of the information for this course can be found in the Introducing Cisco Data Center Technologies official cert guide. It is in its third printing as of September 2015 and can be purchased individually or as part of the official cert guide, which is what I did. Introducing Cisco Data Center Technologies is comprised of 6 distinct groups that are going to be tested to a certain weight. The last 2 weeks we've done Cisco Data Center Fundamental Concepts, which is worth 30% of the test. Today we're going to do the Data Center Unified Fabric, which is worth 20%, and it's going to be finished today. Then we're going to go to storage networking, which is worth 18%, where somebody's going to be taking over, followed by unified computing for 17% and data center virtualization at 14%. There's also a 1% block of data center network services, so they can ask you an annoying question about something you're not going to want to know the answer to. Okay, describe data center bridging in FCoE. Data center bridging is basically a protocol for allowing the Fibre Channel protocols to be able to communicate between DCB-enabled switches and other devices. The traditional Ethernet protocol doesn't support the transport characteristic required to implement storage area networks. You have to have the ability to provide lossless traffic delivery, a necessary bandwidth and traffic priority services in order to make sure that the storage traffic can get to and from its locations without any delay. The following enhancements to the Ethernet protocol were defined in order to meet the demand for unified fabric implementation for network and storage traffic that are going to be transported over the same links. And they're all part of the data center bridging protocol. First one is priority flow control, which is defined by IEEE 802.1q BB. Enhanced transmission selection, which is defined by IEEE 802.1q AZ. Quantized congestion notification, defined by IEEE 802.1q AU, and the data center bridging exchange, defined by IEEE 802.1 AB, which is part of the LLDP class, and it has TLV extensions. The TLV extensions are type, length, and value, and it provides the ability for additional capabilities for the data center bridging exchange. Priority flow control is because Ethernet protocol doesn't have any guarantee of delivery. Ethernet typically relies on higher level protocols such as TCP to retransmit lost traffic, and it defines the flow control mechanism under the IEEE 802.3x standard. That standard actually provides the ability to pause frames for the entire physical link and has absolutely no ability to selectively pause class of service, which is important for FCoE. The priority flow control provides lossless Ethernet transport services for Fibre Channel over Ethernet, and it enables per class of service level pausing based on per 802.1 class of service levels. So basically what can happen is as the picture implies, is the data is coming into the Fibre Channel forwarder and is passing it across the Ethernet link. When that second switch gets it and it actually fills its queue, it can send a pause frame back to the original switch telling it to, hey, stop sending me more traffic, because it doesn't have the ability to drop packets. FCoE is supposed to be lossless, so it will actually queue up, it'll send a pause frame back to the first switch and wait to empty its buffer to send it an unpaused frame so they can start sending traffic again. And that behavior can cascade across the entire network. So if you're talking about multiple hops between multiple data center DCB-enabled switches, that can cascade all the way back until it reaches the source, and the source will actually stop sending the traffic. Enhanced transmission selection. It enables optimal QoS strategy for links between data center bridge-capable switches and bandwidth management for virtual links. It can create priority groups that allow traffic belonging to the same priority flow class to a service to be treated individually and differently. The bandwidth allocations are based on minimum guaranteed bandwidth, not a maximum guaranteed bandwidth. So you can still have that bursty traffic. So in this case, if you're looking at the traffic coming in, assuming that we're allowing 4 gig for LAN traffic, 3 gig for storage traffic, and 3 gig for server traffic, as the first timer hits, it gets sent over here for 3, 3, and 3. So nothing's being changed, it's allowing all the traffic through. As the timer 2 hits, and we're still sending 3 gig of traffic for the first two classes, but we've raised the third class to 4 gig, it expands to fill that void there. On the third one, when the server cluster traffic drops to 2 gig, but the storage traffic remains the same, but the LAN traffic goes to 6 gig, we still get the full 3 gig available. We only consume 2 gig, and even though it's a 10 gig link, the LAN traffic can, even though it's guaranteed 4, can go to 5, not to 6. It can go to 5 because it's been guaranteed 4, but the other 2 were guaranteed 3 each, and one of them didn't use one of them, so that it'll just equal 10, and it'll consume whatever is available in its class. The default behavior of Cisco switches supporting DCB standards is assign 50% of the interface bandwidth to the FCoE no drop class. Quantized congestion notification. So with QCS, the PFC, which enables you to throttle down transmission for no-drop traffic classes between 2 adjacent capable switches, QCN does it slightly differently. It's defined by IEEE 802.1 QAU, and it applies congestion notification directly towards the source without using the intermediate switches, and it uses the source MAC address for that. So what it attempts to do is, in the second hop here, it maintains a congestion. So what it'll do is it'll send a QCN message straight to the initiator, in this case, telling it that you need to slow down. It doesn't send it to the intermediary switch, it sends it right back to the source, and that is going to be based on the MAC address. That way it can only affect certain parts of the network, causing the congestion. The wrinkle with QCN is that since FCoE protocol operates at layer 2 and is encapsulated in Ethernet, it has a function called MAC address swapping. So the Fibre Channel forwarders, as it goes from point to point, it decapsulates the Ethernet frame, looks at the Fibre Channel frame, and then makes a forwarding decision. Then it re-encapsulates the Fibre Channel frame with new Ethernet headers. And when it does those new Ethernet headers, it actually inserts its own MAC address as the source, and the next hop is MAC address as the destination. So it more like routing. So in a normal layer 3 network with IP switches, each time it goes to through a routed hop, it's going to replace the IP header with the source and destination. When it gets to the end, with the MAC addresses between the beginning and end, when it gets to this layer 2 MAC swapping, it's routing on a per hop basis, but it's using the MAC addresses. Not all Nexus switches are capable of supporting QCN because it doesn't have a lot of value added when compared to priority flow control. Since it's already going to be doing the MAC address swapping, priority flow control goes hop by hop, whereas the QCN, if it goes to an intermediary switch because of MAC swapping, it's going to hit the very last, the very next the intermediary switch regardless. It can't go back to the source. Data center bridging exchange. It's a negotiation and exchange protocol between the FCoE initiator and target and the DCB capable switch, or between two DCB capable switches. Typically, the initiators are going to usually be a server. Targets will usually be your storage array. It's an extension of the link layer discovery protocol defined under IEEE 802.3 AB standard, and it performs a number of discovery functions on adjacent switches and endpoints. So it looks for configuration mismatches, and it negotiates link parameters. So it's going to negotiate behaviors for priority flow control, enhanced transmission selection, network interface virtualization, and it's going to monitor logical link up, down, and make sure they're successfully negotiated.
Hey, Shane, got a question here. Is it,
Sure.
I'm maybe a little behind, but is it a higher latency COS of NCAP and DCAP, or is it line rate?
I missed the first part of the question. What is that?
Is it higher latency COS of NCAP and DCAP, or is it line rate?
As far as I'm aware, it's line rate. I'd have to look it up, to be honest with you. It's probably, and it might be different on a platform by platform basis.
Okay.
So Fibre Channel over Ethernet is where Fibre Channel protocol has been wrapped in Ethernet headers. Fibre Channel protocol is established as one of the more best reliable and best performing protocols for storage traffic. I'm sure that's going to cause some people some consternation in different camps, but realistically, from a storage standpoint, Fibre Channel is the Cadillac of protocols. Fibre Channel over Ethernet simply uses the Ethernet transport to forward the Fibre Channel frames across the unified fabric. The FCoE standard leverages traditional Fibre Channel protocol, but allows it the flexibility of running on top of the high-speed Ethernet fabrics. It's an essential building block of the Cisco Unified Fabric architecture for converging network storage traffic over the same Ethernet network. So the Fibre Channel overnet logical endpoints, they're responsible for the encapsulation and de-encapsulation functions for the FCoE traffic. With FCoE, they don't alter the higher level of the protocol stack, so they remain fairly unchanged. To higher level system functions, FCoE appears as a standard Fibre Channel network, which allows all the tools in the native Fibre Channel environment to be used in an FCoE environment. The environment has 5 layers, starting at layer 0 and working its way up. The physical layer and the transmission protocol layer map to OSI layers 1 and 2. And then you have some FCoE mapping. Beyond that, at the higher level, those are going to be identical to the Fibre Channel protocol. FCoE works on port types. Each port type has a specific role in FCoE solutions. They map very closely to the ports that are in a standard Fibre Channel network. They have FCoE E nodes that are either initiators or targets. Initiators, again, are usually going to be your servers, and targets are always probably going to be your storage arrays. The E nodes are going to prevent a port that they call VN port type that connects to a virtual VF port. So the VN is for network or node, and VF is for fabric. So node ports connect to fabric ports. So in this picture, virtual node port is connected to a virtual fabric port, and this virtual fabric port is connected to this node port, and this is providing the connectivity between the initiator and the target storage array. The same behavior on the Cisco MDS 9000 switches in traditional Fibre Channel. You have the N ports to the F ports to the N port. They perform basically the same function. The first hop switches, like the Nexus 5000, can operate in either full fiber channel switching mode or in FCoE NPV mode, which we'll talk about a little bit more in a little bit. And again, the FCoE port types closely resemble the traditional fiber channel port types. And there are several other port types that we'll get into a little bit later. FCoE nodes, they're a combination of the logical endpoints and fiber channel protocol stack on converged network adapters. They create at least one VN port facing a VF port, and each VN port has a unique eNode MAC address. It's dynamically assigned by the Fabric Channel forwarder during the Fabric login process. That Fabric provided MAC address is 48 bits and it consists of two 24-bit fields. One is the FCoE MAC address prefix, which is FCMAP, and the Fibre Channel ID. There are 256 FCMAP values that are available, in order to be able to provide non-unique Fibre Channel ID addresses. The recommendation is to not build different fabrics into the same VLAN for FCoE, just to avoid the duplicates and having to use the FCID addresses to ensure that the FCMAP to make it sure that the FCID addresses are unique. The Fibre Channel forwarder, it's a logical fiber channel switch entity residing inside an FCoE capable Ethernet switch. It provides the intelligence to enforce not only the fiber channel protocol, but also the forwarding path, and makes all the forwarding decisions between itself and other data center bridge switches or targets and initiators. The FCoE fiber channel forwarder is responsible for host fabric logins and encapsulation and decapsulation of the traffic. And usually there's going to be at least one, possibly more, logical endpoints that are internally in the switch to attach the Fabric Channel forwarder to the Ethernet switch itself. The FCoE encapsulation, the main part of this is that it's wrapped in a normal Ethernet header, layer 2 header. So the FCO packets must exchange in the context of a VLAN. There's an 82.1q tag as part of the header. FCoE VLANs are going to be mapped to Fibre Channel vSANs. So vSANs for Fibre Channel work a lot like VLANs, and it's a way to separate your domains. The next block with storage is probably going to talk a lot more about vSANs, but generally they're a way of separating out different storage domains. Nexus 5000 switch FCoE requires a dedicated VLAN. You can't use a VLAN for a FCoE VLAN and something else. It has to be dedicated to that function. An FCoE frame can be up to 2,180 bytes, so jumbo frame support must be enabled. And the Nexus 5000 series switch requires the manual creation of a class FCoE default system class prior to enabling the FCoE. And that's because when the FCoE is enabled on the 5500, it defines an MTU of 2240 bytes to that class. So it has to be there for it to do that assignment when FCoE is turned on. FCoE has an initialization protocol. It's the control plane protocol. It's responsible for establishing and maintaining fiber channel virtual links between pairs of adjacent FCoE devices. Establishing virtual links has three primary steps. Discovering the FCoE VLAN, discovering the MAC address of the upstream Fabric Channel forwarder, and performing Fabric login and discovery operations. And it runs continuously verifying reachability. The VLAN portion for discovering VLAN is not part of the standard. It doesn't have to happen. If you manually create the FCoE VLANs, it won't do the discovery. Converged network adapters. Usually you're going to see them in servers as a PCI Express adapter. It's going to contain the functions of a traditional host bus adapter and a network interface card in the same card and form factor. CNAs are also available in mezzanine form factor for blade systems, and they're required to operate at 10 gigabit per second or more. They are presented to the operating system as two separate devices. So in traditional server networking, you're going to usually have a host bus adapter, and it's going to have its own driver for Fibre Channel, as well as the NIC was going to have its own Fibre Channel, its own Ethernet drivers. Same thing with the CNA. Even though those functions are combined into a single hardware card, the operating system treats those as separate entities and uses distinct drivers for each And with CNAs, both network and storage traffic is sent over a single unified wire connection from the server to the upstream first hop access layer switch for Fibre Channel. So FCoE speed, with the Ethernet speeds increasing at the pace that they are, we're already looking at a fairly decent rollout of 100 gigabit Ethernet now. Compared to Fibre Channel, it's gotten a lot more adoption more quickly in terms of higher speeds.
Hey, Shane.
Sir.
Yeah, we have a question for Graham. He's asking, is Fibre Channel over Ethernet routable? And if not, what's the max number of hops?
It doesn't do routing. The routing on Fibre Channel is usually done by, you can do a function called inter vSAN routing. It's a function of your Fibre Channel switch. It doesn't do routing. It only does layer 2. I'm not aware of.
No, he was asking about Fibre Channel over Ethernet.
Yeah, no, I understand. There is
okay.
So there's a direct correlation between the two protocols, and as far as I'm aware, there may be a upper limit to how many hops that it can do. I don't know exactly what those are. I can look them up, and it may be different on a platform by platform basis. I'm not sure if the protocol itself has a defined maximum number of hops, but most likely it's going to be the same as traditional Fibre Channel. And that domain, the scaling of that domain is going to be based on the fabric IDs and the domain IDs. All right, so with the Fibre Channel speed, with 8 gig Fibre Channel, they have a different encoding scheme. So even though the 10 gig FCoE is only 2 gigabits per second higher from a rate standpoint, the throughput is actually 50% more than the 8 gigabit Fibre Channel. And then when you start getting into the higher rates between 16 gig and 40 gig, the 16 gig Fibre Channel uses the same encoding as 10 and 40 gig, but it's only 33% faster than 10 gig, and 40 gig is 300% faster than 16 gigabit Fibre Channel. The throughput is just scaling, and it's going to continue to grow with Ethernet. And virtual interfaces and fabric extenders. So the fabric extender architecture with FCoE, the FEX provides an extensible and scalable fabric solution based on IEEE 802.1 BR standard. It's a bridging standard. It provides adaptive server and server adapter agnostic architecture. It simplifies operations with investment protection. It provides a single point of management and policy enforcement. Scalable 1 gigabit Ethernet and 10 gigabit Ethernet server access, low and predictable latency, extended and expanded switching fabric access layer, and reduced power and cooling. Well, one of the things that the FEX do well is it acts as a extended line card. So the intelligence is in the parent switch, and all of the features are located in the parent switch. So as you make your configuration changes and you enable features, those features are automatically going to be drilled down into whether it's the hardware FEX or the Adapter-FEX. That gets pushed down into those fabrics. So with the Cisco 2000 series FEX, it's a hardware appliance. It was an extension of the unified fabric to the top of rack. A lot of times you'll see Nexus 5000s or 7000s maybe in a middle of row or an end of row implementation, and rather than having to spend the money to put a series of 5500s on the top of the racks all the way down, you can do fabric extensions by deploying these Nexus 2000s, whether it's 2232 or 2332 for 10 gig or 2248s for 1 gig, and spread them all the way down throughout your data center and extend that fabric. It allows you to create a unified fabric with a single point of management at the head end. The physical FEX interfaces are represented as logical interfaces on the parent switch. All your operations, administration, and management functions are going to be performed on the parent switch. And the FEXs have no local switching capabilities. So all the traffic is going to be forwarded to the parent switch. So that means is that even if you have a fabric extender, and let's say it's a fabric extender 101 and it's connected to an upstream switch, the port 1 and port 2 might have two servers that are communicating directly to each other, but their traffic is still going to leave the FEX, go to the parent switch, and come back down. There's no local facility for the FEX to transfer that data from one server on one port to another server on an individual port, even in the same port group or on the same FEX. It can be attached to a single parent in straight through. It can also be connected to multiple parents in a VPC topology. In straight through FEX attachment topology, the FEX is connected to a single parent switch. It's going to manage the FEX exclusively and provide all of its features. The FEX can be connected via a single link or through a port channel up to the maximum number of uplinks available on the FEX. Most FEXs are going to come with 4 or 8 uplinks. The uplink interfaces that are going to the parent switch are going to be known as the network interfaces. Downstream facing interfaces that are known as host interfaces. And as long as a single network interface uplink exists to the parent switch, the FEX is going to remain registered. And the number of network interface connections is going to directly determine your oversubscription. So in this example for oversubscription, we have a Cisco Nexus 2232 PP. It's going to have 32 10 gigabit host interface ports and 8 10 gigabit network interface ports. So the total amount of bandwidth facing the host are going to be 320 gigabits per second. And the most bandwidth you can have going north upstream is going to be 80 gigabits per second. So if you fully populate the host interfaces and you have a single network interface connecting to the parent switch, your subscription is going to be oversubscription is going to be 32 to 1. If you go to 2 network interfaces, it's going to drop it to 16 to 1 and so on until you get them all to 8 and 4. You're going to want to do everything in powers of 2. Otherwise, you're going to have a bad hash algorithm for uplinks. You want to use as many, excuse me, you want to use as many network interface uplinks as possible with FCoE FEX to reduce the pause frames and overall slow storage connectivity. FEX straight through has a scenario called static pinning. Static pinning is where we're going to map the host interface ports to specific network interface uplinks. In this case, if you have a network interface uplink fail, the FEX is going to disable any host interface that's been pinned to it. So servers attached to the host interface is going to see their Ethernet link go down, triggering a failover if the failover is available. In this example, all 8 links are being used northbound on the host interface on the left. Port 5 is going to be part of the pin group to network interface 2, so most likely 1 through 4 is on pinned to 1, 5 through 8 is going to be pinned to 2. So when that link goes down, this server, which happens to be on 5, is going to lose that link, and it's going to have to fail over to the other fabric extender. And in this case, if there are 4 servers on it, it's going to lose all of them. If they're connected by that second interface in a different pin group, or if they're on a second FEX, they're going to maintain their connectivity from the failover. If they're connected via a single link to the disabled pin group, they're going to lose connectivity until that failure clears. And the reason why they sometimes do static pinning is because it maintains the oversubscription ratio. So for the 8 links here from the 32, every 4 are going to be tied to a network interface. No matter how many links you lose from the network, you will lose the appropriate amount of host interfaces to maintain that same subscription ratio based on how many uplinks that you physically have working. You can also do dynamic pinning. In that pinning mode, you're going to use a port channel that's going to be used to pass traffic between the FEX and the parent switch. Failure of a single port channel doesn't bring down any of your host interfaces. If a port channel member does fail, the traffic crossing the FEX is just going to be hashed across the remaining members of the port channel based on whatever hashing algorithm you've chosen. That behavior reduces the overall uplink bandwidth, and which is why it would create a higher oversubscription rate. The oversubscription rate is important, especially when you're talking about combining Fabric Channel over Ethernet and your regular Ethernet traffic, because now you have to account for both classes of traffic. You have to account for the bandwidth being used by your regular network traffic, especially your servers that are going east-west, but also your servers that are using the storage infrastructure. It's all going over the same wire, so you have to account for all of that, and your oversubscriptions, if they grow too high based on failures, you can start losing connectivity and have slower storage networks. You can attach it to two parent switches that are participating in a VPC domain. So in this case, you're going to have redundancy from each FEX to two different parent switches instead of having them singly home to one upstream switch. Both parent switches are going to manage the ports on the FEX and provide its features. As long as you have a single link to one parent switch, it'll maintain the FEX registration and it'll keep all the host interface ports enabled. VPC FEX topology doesn't support static pinning. Since they're going to be using port channels to connect to two different switches in a VPC domain, it's going to treat it as a single link and it's going to load balance across them. In this case, for them to maintain connectivity and register with the parent switches, there's a certain number of configuration parameters that have to be identical on both parent switches, including port channel mode for the ports, for the FEX ports, link speed for the port channel, duplex mode, trunk mode, the spanning tree protocol mode, the spanning tree protocol region configuration if you're using MST, the enable or disable per VLAN state, static spanning tree protocol global settings, quality of service configuration and parameters. And in turn, servers that are capable of establishing port channels off the FEXs can use VPC connection to a VPC connected FEX. And that's a dual layer VPC, and that's going to be what they call enhanced VPC. So now you're having a VPC down to your server, to the FEX, and then from the FEX to the parent switches. We are also going to look at FCoE traffic pinning in an enhanced VPC topology. So in standard Fibre Channel, traffic is usually going to be split between two distinctly different fabrics, and they don't ever meet. So in FCoE, they suggest that you do the same thing. So you're going to want to pin FCoE traffic from a specific FEX to a specific parent. So to do that, you have to enable FCoE under a single different FEX on each parent switch. So in this case, side A is 5500A. And each of those, it has two FEXs connected to it, and it's going to be FEX 101 and FEX 102. Since they're both connected to it, we want to be able to pin FCoE traffic A to this side and FCoE traffic B to this side. And so they won't transport across these links to the parent switch. To do that, we have to go into each of them, and under the FEX configuration, we have to enable FCoE on the parent switch just for the FEX that we want to have FCoE traffic coming to the parent switch on. Adapter-FEX is where they virtualize the PCIe bus and present virtual adapter to an operating system for both network and storage connectivity. It can be connected directly to a parent switch or connected to a FEX. If it's a FEX connected to another FEX, it's referred to as a cascading FEX topology. There's no licensing on the 5500 to support Adapter-FEX, but it is a feature set that has to be installed and enabled. To install it, you just install feature set virtualization and install feature set, and then enable feature set virtualization. And this virtualization allows you to have your FCoE server connected directly to the parent switch, connected to a FEX, connected to a straight through port group to a single switch, or to the VPC domain. The Adapter-FEX allows the instantiating of virtual network interface cards to the server interface mapped to a virtual Ethernet interface on the upstream switch. This enables you to create features such as ACLs, private VLANs.
Hey, Shane?
Sir?
We got a question from Graham. He's asking any minimum version of NXOS.
For the virtualization?
I'm not, for Adapter-FEX.
Yeah, I'm sure that there is a minimum one. I'm going to guess it's somewhere around 5.2. I'd have to look up the exact one depending on the platform. All right, so I'm going to have to look it up a little bit later because it's not coming right up for me. So before the EV interfaces can be created, the physical Cisco Nexus switch is going to have a VN tag mode on each of its physical ports. The VN tag mode is going to allow the virtual network tags to come through and enable multiple virtual Ethernets to be bound to a specific physical interface on different channels. The data center bridging exchange protocol is also going to have to run between the Nexus switch interface and the connected server. Excuse me. Once the VN tag mode is activated, the server starts to include network interface virtualization capabilities, type length value fields in its data center bridging advertisement. So that's how it's going to pass the information between the two devices and the Adapter-FEX to start either using the manual configuration to create the adapters or the dynamic configuration to create the adapters. To provision a virtual Ethernet adapter, you can do it either statically or dynamically. Static adapters can be configured on the switch in advance, so you don't have to wait for the server admins to do their part. You can configure them in advance, and when the server admin joins the channel with and creates their Ethernet interfaces, the interfaces on the switch will already be there. They're going to have a channel, specific channel, and they have to match between the switch and the server. Dynamic Adapter-FEX provisioning is going to be based on port profiles. And port profiles are communicated to the CNA through the VIC protocol. Usually the dynamic virtual Ethernet interface numbering is going to start above 32.768. To provide static virtual Ethernet interface provisioning, you create the virtual interface, provide it a number, and then you bind it to a specific physical port and assign it a channel. To do that to all your virtual interfaces can be prone with human error, so they suggest performing port profiles. Port profiles can be configured once. You provide a port profile type V Ethernet, provided a name. In this case, this is going to be NIC VLAN 10, and then you provide it the configuration. You tell it it's switch port access VLAN 10, switch port mode access, and enable it. Once it's enabled, the dynamic provisioning goes into play. You can tell to inherit the port profile, whether it's VLAN 50 or VLAN 60 in this case. You provide them separate channels, but you can bind them to the same interface. So in this way, you can have the same physical interface on the switch, support multiple virtual Ethernet interfaces in different VLANs. Virtual fiber channel interfaces are the equivalent to regular fiber channel interfaces. They can be shut down without having any effect on the virtual NICs interfaces, even though they're on the same CNA. Adapter-FEX virtual NICs and HBAs are separate logical entities, and they must be bound before they can be used. So what happens is you must create the Ethernet physical switch with a VN tag. You create the virtual Ethernet, in this case 10, bind it to a specific physical Ethernet on that channel, make it a trunk, and then allow VLAN 50. VLAN 50 is going to be the FCoE VLAN. And then for the virtual fiber channel interface, provided the virtual interface virtual fiber channel 10, you bind it to the Ethernet interface and then turn it on, and that maps it to the Ethernet, which in turn maps it to the vSAN. Virtual interfaces can have redundancy either in the OS or outside of the OS. The Adapter-FEX allows for failover that doesn't involve the operating system at all. Fabric failover is available on Cisco UCS Blade and rack servers. Excuse me. Each VNet can be associated with both physical interfaces on the virtualized CNA. create the same VN tag and the same VN channel to each of the physical interfaces on the converged network adapter and the VETH interface. But for FCoE connectivity, the instantiated HBOs don't leverage fabric failover functionality because it's still going to maintain the separation.
We got a question?
Sure.
Are only Cisco physical CNA supported or third-party ones like QLogic? And are we only talking UCS only?
In terms of the exam, we're talking UCS only, but there are QLogic and emulators make Adapter-FEXs that are certified to go into the UCS servers. And there's probably a few others, but those two are the bit larger ones. So with FCoE, we've talked about the Fibre Channel over Ethernet when we're talking about maybe a single switch being in between the initiator and the target. There's also multi-hops, so sometimes you're going to have a much larger scale Fabric Channel infrastructure, and it needs to be able to scale and it needs to be able to support Fabric Channel over Ethernet across multiple switches. So multi-hop unified fabric carries network storage traffic in a converged manner across an Ethernet beyond single hop topology. Various topologies exist for multi-hop. These topologies offer consolidation at different tiers of the data center. The first one is the first hop access layer consolidation. And in this access layer, the consolidation reduces the number of adapters and switching platforms to accommodate network and storage connectivity. So where normally you might have multiple HBAs, ports, and multiple network adapters going to a different switch or a different fiber channel switch, now they're combined in a unified wire and carrying both FCoE VLANs and data VLANs to the switch. For larger environments, the Nexus 7000 switch can be used for direct server connectivity, and it has a VDC function from what we talked about last week with the storage VDC with shared adapters. And with the shared interface, as the servers are sending the data and the FCoE VLANs northbound on the unified wire to the shared interfaces, the switch does a ether type lookup, and if it's an FCoE or an FIP ether type, it's going to send it directly to the storage VDC, and if it's any other ether type, it's going to send it to the data VDC for the network traffic. At the aggregation layer, the consolidation occurs when the aggregation layer is going to be processing both network and storage traffic coming from the access layer. Normally, in this case, with a larger environment and multi-hop, it may be a spine and leaf configuration where the aggregation layer is pulling in multiple leafs from the access layer and aggregating all of them in tandem to deliver a scale-out unified fabric solution. The aggregation layer consolidation is typically achieved by leveraging a separate set of cables between the access layer and the aggregation layer fabric switches. But to support multi-hop FCoE behavior, access layer switches have to employ one of three modes of operation, either FIP snooping, endpoint virtualization, or full fiber channel switching. FIP snooping is a traditional fiber channel node, logs into the fabric via point-to-point links. But in FCoE, there might be multiple hops, and normally it's going to be point-to-point, but when there's multiple physical hops, it'll be a logical point-to-point connection. But there is an opportunity, because of the multiple physical hops, that someone could do fabric channel forwarding MAC spoofing. So the snooping feature helps prevent man-in-the-middle spoofing attacks. The FIP snooping bridges are capable of inspecting those messages between the fabric channel over Ethernet server and the fabric channel forwarder. Then it's going to dynamically create an access list to ensure that those communications remain point-to-point. But it's very limited in terms of Cisco switch support. I think one of the only Cisco switches that support it, I believe, is the 4000, which is a blade switch for an IBM blade center. FCoE NPV is an enhancement of FIP snooping functionality, and it still provides the secure method to connect the FCoE capable host to an FCoE fiber channel forwarding switch. FCoE NPV doesn't have the management troubleshooting issues that are inherent to managing hosts from the fiber channel forwarder, because the fiber channel over Ethernet NPV implements FIP snooping as an extension of its function, and it enables communication through fiber channel and FCoE ports at the same time. They also don't consume a fiber channel domain ID. So when you're doing fiber channel networking and you have multiple switches in a fiber channel domain, each switch that's doing full fiber channel switching is going to consume a domain ID. Those domain IDs are limited. I believe it's somewhere around 256, so it reduces the scale. The endpoint virtualization function is going to allow that to not consume that ID, and it's going to virtualize the floggies from the inbound servers at the access layer and forward them up to the fabric channel forwarders at the aggregation layer. Enabling the NPV feature requires a license, and there's two methods to enable it. The first method is the scary one. If you want to enable FCoE and then enable NPV separately, from the global config, you can type feature FCoE and feature NPV. The problem with this particular feature is if you do it that way, it is going to write erase your switch and it's going to reload it. To enable them together, you can just enable feature FCoE NPV and it will not erase and reload the switch. Under full fiber channel switching, the switches are going to use a virtual edge port between the unified access and aggregation layers. The VE ports are going to interconnect the fiber channel forwarders in the multi-hop topology of the unified fabric. The VE ports are capable of carrying multiple vSANs, so they should be defined as trunks if you're going to do multiple vSANs, and therefore inter-switch links. These are fully functioning fiber channel switches that participate in the fiber channel fabric and pass information to and from the forwarding, and can be used, and they're going to collect zone information for the initiators and the targets that are allowed to talk to each other. In order to configure a VE port channel and trunk configuration, in this example, we're taking physical interface Ethernet 1 to 2 and creating a port group out of it, giving it port channel ID number 10. Under that port channel, we're going to switch port mode trunk and allow VLAN 5, which is the FCoE VLAN 5. That maps directly to vSAN 5. Then we're going to create the virtual fiber channel port channel, give it ID of 10, and make it switch port mode E. We want to be able to eventually do multiple vSANs over it at some point, so we're going to make it a trunk, but we're only going to allow vSAN 5, which maps it directly to VLAN 5, which is the FCoE VLAN. The steps are going to be done on both sides, but to maintain separation, you're going to use the different FCoE VLAN as well as the different FCoE vSAN ID. Dedicated wire versus unified wire. Servers leverage unified wire to run both network and storage over a single physical cable. And a multi-hop FCoE connectivity, a lot of times they're going to leverage a dedicated wire approach, and that's where the network and the FCoE storage between the access layer and the aggregation layer are going to have separate physical links, one physical link for network traffic and separate physical links for FCoE traffic. Using the dedicated wire gives you some advantages as far as better traffic oversubscription management for the storage traffic, and it gives you a little bit more room to treat the traffic types differently and provide better monitoring and better management of the traffic. It also lets you do gradual introduction of FCoE into the larger environment, so it'll help you with investment protection. You can run dynamic FCoE over Fabricpath. With Fabricpath, it's going to create a logical rather than a physical FCoE side and an FCoE side for traffic segregation. Since it's using Fabricpath as its underlying transport, it's going to be able to efficiently load balance multi-protocol traffic throughout the data center. And under dynamic FCoE, it's going to establish a relationship between the switches, so the possibility of human error and configuration problems are going to be minimized. And as a spine leaf configuration, as you scale out the data center and you add more switches and more capacity and more links for more bandwidth, it's going to have a better profile for high availability as you increase your scales. The dynamic virtual links in FCoE, all the leaf nodes are going to function as fiber channel forwarders, and it's going to transparently establish an overlay between each of the leaf switches to all the other leaf switches with a virtual link topology over the Fabricpath spine nodes. The Fabricpath spine nodes are not going to participate in any of the FCoE process. They're really just there to facilitate the virtual point-to-points for the VE ports between all of the leafs to all of the other leafs. The FCoE frames are forwarded between the Fabricpath leaf nodes based on their outer destination MAC address. And FCoE fiber channel forwarders implemented by the Cisco Fabricpath leaf nodes are going to be part of the virtual link overlay topology. So in this way, all of the leafs are going to participate with each other, and they're going to use the transport of the Fabricpath at layer 2 to get to each other over the spines. And so they're going to be able to use the shortest path first compute across all the virtual links to ensure forwarding decisions for the FCoE traffic as far as crossing the virtual fabric. And it designates both ends of the FCoE virtual links as port type VE. And those ports are going to be encapsulated with Ethernet and have MAC addresses that are used as a source destination for encapsulation and forwarding. Dynamic virtual fiber channel interfaces. Every FCoE fiber channel forwarder leaf node is uniquely identified by a global fiber channel forwarder MAC address. Every fiber channel over Ethernet fiber channel forwarder leaf node floods an FIP unsolicited multicast discovery to the all fiber channel forwarder MAC address. All fiber channel, sorry, I'm losing my voice. All fiber channel forwarder leaf nodes receive the multicast advertisement on the corresponding VLANs and determine the mode multipath upon receiving it. A dynamic virtual fiber channel interface acting as a VE port is going to be created between the two fiber channel forwarder leaf nodes. Then the dynamic virtual fiber channel interfaces are going to be differentiated based on their interface ID range. And then all fiber channel forwarding leaf nodes are going to be one logical hop away from each other with a default FSPF cost value. And this final slide is just showing that the integration between traditional fabric channel and fabric channel over Ethernet can still be run over the leaf spine technology. Dynamic FCoE enables interconnectivity between traditional fiber channel and FCoE nodes. We have the storage array, which is a traditional storage array, and side A and side B. These are going to be running traditional fiber channel as well as FCoE, so that fiber channel over Ethernet servers can participate in the unified fabric with traditional fiber channel. And that was it. I'm sorry that ended a little bit early. Guess that makes up for the hour and a half I went last week.
I guess we don't have any questions for tonight.
Yep, I'm sorry. I'm just losing my voice, so it's difficult to talk. But I appreciate you guys having me, and I hope that you get us some good information out of it and pass the CCNA data center at some point.
Yeah, thanks for being here and presenting tonight. Learned a lot.
No problem. Thank you, everybody, and have a great night.
All right, good night, everyone.